All right, guys. So today we are going to go over the Unit 6A review. All right, so we'll start with number one. All right, so this is inverse trig functions here. All right, we do have to be mindful that with inverse sine and inverse tangent, all right, we are using the right half of the unit circle only. And we also have to be careful that when we are in quadrant 4, all right, then instead of actually calling them the angles on the unit circle, all right, that we are actually calling them their negative coterminal angles. All right, so 11 pi over 6 is actually negative pi over 6. All right, 7 pi over 4 is negative pi over 4. 5 pi over 3 is negative pi over 3. And 3 pi over 2 is negative pi over 2. Okay, so with that in mind, here we have inverse sine of negative square root of 3 over 2. All right, and I guess I should pull up a unit circle here for everybody to look at. Is going on that circle. Okay. This looks like a good one. Okay, so here's our unit circle. All right, so basically this is saying, all right, on the right half of the unit circle, where is sine negative square root of 3 over 2? All right, so we go here. We say, okay, we're looking on the right half of the unit circle. All right, sine is my y coordinate. All right, so where is my y coordinate? Negative square root of 3 over 2. That occurs right here, all right, at 5 pi over 3. But remember, we aren't allowed to call it 5 pi over 3. We have to call it its negative coterminal angle, which is negative pi over 3. So that's all you have to answer for this. And we're done. All right, so very straightforward. All right, so same thing here, inverse sine. All right, so we are only concerned about the right half of the unit circle. All right, and now we're looking for where is sine 0. All right, so again, right half of the unit circle, y coordinate. 0 is right here. Oh, well, that occurs at 0. This just equals 0. All right, C, inverse cosine of negative 3, or negative square root of 3 over 2. All right, now inverse cosine only deals with the top half of the unit circle, and we never have to worry about adjusting any of the angles like we do with inverse sine and inverse tangent. All right, so inverse cosine is the top half of the unit circle here. All right, cosine is the x coordinates. All right, so where is my x coordinate? Negative square root of 3 over 2. That happens right here at 5 pi over 6. So my answer is 5 pi over 6. All right, D, inverse cosine of positive square root of 3 over 2. All right, again, inverse cosine is the top half of the unit circle. All right, so we go to the top half of the unit circle and say, where is my x coordinate? Positive square root of 3 over 2. That happens right here at pi over 6. All right, inverse tangent of 1 over the square root of 3. All right, now this is not rationalized. All right, so you can really think of this as the inverse tangent of the square root of 3 over 3, if we go ahead and rationalize that. All right, now on our unit circle here, all right, there is no tangents, all right? But remember, to get the tangents, you just take the y coordinate and divide it by the x coordinate, all right? Inverse tangent is still the right half of the unit circle. 1 divided by 0, whenever you divide by 0, you're undefined, right? Square root of 3 over 2 divided by 1/2 is just the square root of 3. Square root of 2 over 2 divided by the square root of 2 over 2 is 1. 1/2 divided by the square root of 3, when you rationalize, is square root of 3 over 3. 0 divided by 1 is 0. And then these are going to be the same. You just flip them and they'll be negative. So this will be negative square root of 3 over 3, negative 1, negative square root of 3. Of course, this is still undefined. Okay, so our current problem here asked, all right, where is my tangent? Square root of 3 over 3. So we go back here. Positive square root of 3 over 3 occurs right here at pi over 6. So this is equal to pi over 6. All right, here for f, we have the inverse secant of negative 2. Secant is not one of the things on our unit circle, right? However, all right, we should know that, secant of theta is equal to 1 over cosine of theta. All right, so, we can actually kind of go ahead and think of this very similarly. Now, in terms of, the pure math of it, you don't have to go through this every time. I just want to show you why this works. All right, so we want to know what this equals, and we know that it's going to equal some angle theta, right? Because when we do inverse trig functions, our answer is an angle. All right, well, how do I undo an inverse trig function? Anybody remember? If not, you're really going to struggle on this test.
Use the regular trig function.
Absolutely. You use the regular trig function, all right? So if I take the secant of both sides, the secant and the inverse secant will cancel, so I'm left with negative 2 is equal to secant of theta. All right, well, now because of this here, all right, I know, okay, well, if secant of theta is negative 2, all right, then cosine of theta is negative 1/2. All right, but again, I'm trying to get to this inverse inverse trig problem here. So I want to undo my cosine. So I do inverse cosine of both sides. So those will cancel out. All right, so now I have the inverse cosine of negative 1/2 is equal to theta, all right, which the angle is what I'm looking for. All right, you don't have to go through and show me this every time. Basically, all that happens is whatever trig function like we're dealing with that we don't like, namely cosecant, secant, or cotangent, all you have to do is take its reciprocal inverse, all right, and then also take the reciprocal of the argument. Okay, so you can really jump straight from here to here. I just wanted to show you why it works that way. All right, so what we're really looking for here is the inverse cosine of negative 1/2. Inverse cosine, again, is the top half of the unit circle. So we look at the top half of the unit circle and say, where is my x coordinate? Negative 1/2. All right, so here's my top half of the unit circle. Where's my x coordinate? Negative 1/2. It occurs right here at 2 pi over 3. So this is simply equal to 2 pi over 3. Again, all of this you don't really need to show. I just wanted to show you why it works. Right? You can really just jump straight from here to here. Any questions or concerns on number 1? Excellent. All right. Number 2. All right. Find the exact value of each expression. All right. Now, we just talked about how trig functions and their inverse cancel each other out. All right, but remember, because inverse trig functions are weird, and why I say weird is because in order to even get an inverse trig function, we had to restrict the domain of the regular function. All right, so those of you that were in class that day, or hopefully the rest of you watched the video, right, I showed like the graphs of them and like, okay, well, this doesn't pass the horizontal line test. All right, so we had to kind of only look at a certain section to force it to pass the horizontal line test. All right, so that kind of screwed things up a little bit. So the secret to here is, all right, we always want to look at the inside first. All right, so here we say, okay, here is the inverse sine of 5 pi over 6. All right, now it's important to remember that the domain for inverse sine and inverse cosine is -1 to 1. All right, for inverse tangent, it's all real numbers, so we never have to worry about that. All right, is 5 pi over 6 between -1 and 1? No, right? I mean, pi is 3.14, so even if you just estimate it at 3, 5 times 3 is 15. 15 over 6 is definitely not between -1 and 1. All right, so we can't even do this. All right, so we just say this is undefined. All right, B, arc cosine of 7 pi over 4. Now, what's different about this problem and the previous one? Not counting that it's cosine instead of sine. Yes, the inside is the regular cosine, not the inverse cosine. All right, so we still want to go from the inside out. So I want to ask myself, okay, what is the cosine of 7 pi over 4? So I can look at my unit circle. I go here to 7 pi over 4. Cosine is my x coordinate. All right, well, that is the square root of 2 over 2. So now I can say, okay, remember arc cosine is the same as inverse cosine. So this is really the inverse cosine of the square root of 2 over 2. Right? Well, now this looks like a problem like we just did in that last little section. All right? Inverse cosine deals with the top half of the unit circle. So I'm going to look at the top half of the unit circle and say, okay, where is my cosine square root of 2 over 2? Of course, cosine is my x coordinate. So that occurs right here at pi over 4. All right, so the answer to this is pi over 4. All right, letter C, we have cosine of the inverse cosine of 0.9. We want to do the inside first. All right, so we're looking at the inverse cosine. All right, inverse cosine and inverse sine have a domain of -1 to 1. Is 0.9 between -1 and 1? Sure is. That means these things just cancel out, and this just equals 0.9. All right, letter D, tangent of the arc tangent of 32. Now, we said earlier that the domain for inverse sine and inverse cosine is from -1 to 1. All right, but does anybody remember what the domain for inverse tangent is? All real numbers. Is 32 a real number? Sure is. So these are just going to cancel out, and this will just equal 32. Any questions or concerns there?
Mr. Crouch, can you explain the first one again? Why it's undefined?
Sure. Because we're just talking about kind of the domain of some of the inverse trig functions. And the domain of inverse sine and inverse cosine were -1 to 1, which means you're only allowed to plug in numbers between -1 and 1. Okay? Well, 5 pi divided by 6 is not between -1 and 1, right? Because pi is 3.14, all right? So 5 times 3.14 is 15.7. 15.7 divided by 6 is, I don't know, 2.6, 2.7. All right, so that's not between -1 and 1, so you're not even allowed to do it. That's why it's undefined.
Okay, thank you.
You're welcome. Any other questions or concerns? All righty. Then we will move on to number 3. All right, so here, find the exact value of each expression. All right, well, now we're dealing with different trig functions here, so they're never going to just cancel out nicely like in the last section. All right, so this is where we have to use our little trick. We say, okay, let's let u equal whatever is on the inside. So in this case, inverse cotangent of 2/9. All right, well, we don't like inverse cotangent, so we're going to undo that with regular cotangent. So if you take the cotangent of both sides, that leaves us with the cotangent of u is equal to 2/9. All right. So cotangent, isn't really part of our SOHCAHTOA, right? But cotangent is the reciprocal of tangent. So we know that if cotangent of u is 2/9, then tangent of u must be equal to 9/2. Okay, now we were originally dealing with inverse cotangent, which goes along with inverse tangent since they're reciprocals. Right? Inverse tangent deals with the right half of the unit circle, so the first or the fourth quadrant. 2/9 is positive. Is tangent positive in the first or the fourth quadrant? First, right? Everything's positive in the first. All right. So we're going to go, we know that our angle is somewhere in the first quadrant. Guys, do make sure that your angle is always in standard position, which means you're starting, your initial side is the positive x-axis, and then, your origin is kind of the like vertex of the angle. All right, so this is going to be my angle u. On that last test, multiple of you were doing crazy things. You always drop the perpendicular to the x-axis. Some people were making triangles with the y-axis. That messes a lot of things up, so please don't do that. All right, so tangent, according to SOHCAHTOA, is opposite over adjacent. So opposite over adjacent. All right, so then I do a squared plus b squared equals c squared. A lot of you were still messing that up on the last test, and I emphasized it so many times on the review and in class. All right, a squared plus b squared equals c squared. C squared is always the hypotenuse. All right, in this case, we weren't given it to us, but a lot of people just whatever two are given to you, that's a and b for you guys. That is not right in any way, shape, or form. Okay, a lot of you miss a lot of points because you just don't care to realize that c is always the hypotenuse, no matter what. Okay. So in this case, we have a squared plus b squared equals c squared. So this will end up being the square root of 85. Now we let all of this stuff equal u. So really all we're looking for here is the cosine of u. Right? If this stuff all becomes u, which we said it did, right? We're just looking for the cosine of u. Well, cosine, according to SOHCAHTOA, is adjacent over hypotenuse. So this will be 2 over root 85, which of course we're going to have to rationalize that. So that would be 2 root 85 over 85. And that is our final answer. So we're going to do that for all of these. All right, so here I'm going to say, okay, let's let u equal inverse cosine of 2/3. That means the cosine of u is equal to 2/3. Right, cosine deals with the top half of the unit circle, so we're either in quadrant 1 or quadrant 2. All right, this is positive, so we know that we have to be in quadrant 1 again. So here's my, yep, go ahead.
Column 1 and column 4. I mean, not column 4, column 3. Because,
say that again.
How do you determine whether you are supposed to go in column 1 or column 3?
Okay, we're not in columns, we're in quadrants, right? So just like when we have quadrant 1, quadrant 2, quadrant 3, and quadrant 4. Okay, so that's what we're talking about when I say quadrants. All right, now remember, just from what we've been doing this whole time here, right? Especially here, but also here as well, all right, but mainly here, all right? We were talking about inverse sine and tangent only dealing with the right half of the unit circle. Well, the right half is quadrant 1 and quadrant 4. Inverse cosine deals with the top half of the unit circle, right? Remember, the unit circle is just one unit, right? That goes one unit in every direction here, all right? So if you're in the right half of the unit circle, you're either in quadrant 1 or quadrant 4. If you're in the top half of the unit circle, you're either in quadrant 1 or quadrant 2, okay? Now, and then basically from there, it depends on what this number is, right? If you're positive, well, you know you're always going to be in quadrant 1. If it's cosine and you're negative, you're in quadrant 2. If it's sine or tangent and you're negative, you're going to be in quadrant 4. Does that make sense?
Yes, sir. So it's just because the inverse trig functions don't include quadrant 3.
Exactly. You will never have to deal with quadrant 3 when you're dealing with inverse trig functions. And again, that's because of, again, for the explanation, you want to go back and watch the beginning of the inverse trig functions video. But that's because, again, we had to restrict the domain of the original functions to make it pass the horizontal line test so that it would have an inverse function, and it all stems from that. Okay, so here we know that we're in quadrant 1 here. So cosine from SOHCAHTOA is adjacent over hypotenuse. All right, so now we do a squared plus b squared equals c squared. All right, so we're going to have to subtract 4. So this is going to end up being the square root of 5. All right, so because we substituted this stuff here, what we're really looking for is the cosecant of u. All right, well, cosecant isn't one of our SOHCAHTOA trig functions, all right, but cosecant is the reciprocal of sine, all right. So sine, according to SOHCAHTOA, is opposite over hypotenuse. So if we're doing the reciprocal of that, we're doing hypotenuse over opposite. So this would be 3 over the square root of 5, which when we rationalize is 3 square roots of 5 over 5. So that would be our final answer. All right. Let's go up to part C. All right. Same thing going on here. Arc cosine is the same as inverse cosine. So we say, okay, u is going to equal the inverse cosine of negative 3/7. So again, we want to undo our inverse cosine. So we take the regular cosine of both sides. All right, well, I was dealing with inverse cosine. So again, that deals with the top half of my unit circle. So my angle is either in quadrant 1 or in quadrant 2. All right, here, my value is negative. So I know that I have to be in quadrant 2. All right, cosine is adjacent over hypotenuse. Of course, we know the hypotenuse is is never negative. And from my origin here, I went to the left 3. Left is my negative direction. All right, again, I have to do a squared plus b squared equals c squared. All right, so this is going to be 49 minus 9. So this is going to be the square root of 40. All right, but this can be simplified a little bit. Okay, a perfect square goes into here, namely 4. All right, so this is actually going to equal 2 square roots of 10. All right, so now I'm just looking for sine of u. All right, sine is opposite over hypotenuse. So this is just 2 square roots of 10 over 7. And we are done. And part D, same concept. All right, so u is going to equal inverse sine of -3/8. So we undo inverse sine by taking the regular sign of both sides. So we get sine of u is equal to -3/8. Right, sine deals with the right half of the unit circle, so I'm either in quadrant 1 or quadrant 4. Because this is a negative value, I know that I am in quadrant 4. All right, sine is opposite over hypotenuse, and of course this will be the -1 because I'm coming down. All right, again I have to do a squared plus b squared equals c squared. So 64 minus 9 is 55. So this will end up being the square root of 55. And it's positive because I'm in the positive direction here. So now I'm really just looking for secant of u. All right. Secant is the reciprocal of cosine. So if you want to find cosine first, that's fine. Cosine is adjacent over hypotenuse. So this would just be root 55 over 8. All right, so secant is the reciprocal of that. So that's going to be 8 over root 55, but we'll have to rationalize. So 8 root 55 over 55. And that is our final answer. Oh, I don't know. I don't think so. Just because I don't like you. Is that good, dear? Okay. Any questions or concerns over number 3? Right. It's really all about just using that little u substitution trick, right? Let u equal the inside stuff, and then it's just SOHCAHTOA from there. Yes. Written. It's going to be just like this. Okay. Number 4. Write an algebraic expression that is equivalent to cosine of arctangent of x over 2x plus 5. All right, this looks really messy. It's the exact same thing that we did with the last problems, just with variables instead of numbers. Same concept though. So I let u equal the inside stuff. I undo tangent or inverse tangent with a regular tangent. All right, now I make a triangle. Now we don't know, right, whether this is positive or negative. So why would we want to make it harder on ourselves? Let's make it easy. Say it's positive, put in the first quadrant. It doesn't really matter which one you do because it all would depend on the x. All right, so tangent is opposite over adjacent. All right, so to find my missing piece here, I'm still going to have to do a squared plus b squared equals c squared. All right, doesn't matter which of these you make a and b, but this obviously has to be c. All right, so I'll say a squared plus b squared is equal to c squared. All right, so you take the square root of both sides. All right, I don't really care if you leave it like this. If you really wanted to FOIL this out and then add this to it, you could. That's perfectly fine, right? So if you did that, here you would get 4x squared plus x squared would be 5x squared. And then you get 10x plus 10x would be 20x, and then plus 25. Right, so this would actually be your C. All right, so now we're doing that same thing though, right? We let all of this stuff equal u. So we're really just looking for the cosine of u. All right, well, cosine is adjacent over hypotenuse. So this would be 2x plus 5 over all of this mess. All right, now I don't care if you rationalize that. If you really want to, you can. But it's messy enough as it is. There's no reason to make it look even more messy. So, yeah, you're fine. All right, so don't let that problem intimidate you. It looks really hard, right? And I can't even tell you how many students I've had in the past that do all of these perfect, right? And then they get to this one and leave it blank, right? It's like if you can do these, you can definitely do this one. It's the exact same concept, right? At the very least, you can set it up. You may make some silly little, algebraic error, right? But you can at least set it up and go through the motions, and you may lose a point or two for some silly algebraic error, but don't just leave it blank. Okay. 5. Use an inverse trig function to write theta in terms of x. This is probably the easiest question on the test, and for some reason, one of the most missed questions on the test. All right. So it says to use an inverse trig function and to write theta in terms of x. When it says theta in terms of x, it just means you have to have theta equals some stuff with some x's in it. Okay, that's what that means. All right. Well, we know that we're dealing with this angle. All right. I have an expression for this side and the hypotenuse. From this angle, what is this piece in terms of SOHCAHTOA? Opposite. And what is this piece? Hypotenuse. Which trig function deals with opposite and hypotenuse? Sine. So I would say, okay, sine of theta is equal to the opposite, which is x minus 5, over the hypotenuse, which is 15. Now, it says to use an inverse trig function, and I want theta equals some stuff. I haven't used an inverse trig function, but to break apart sine and theta, what do I have to do? What's the only way to undo sine? Inverse sine. Yeah, it's the only way. Like the absolutely only way to undo a trig function is its inverse. Okay. So we say, okay, well, let's take inverse sine of both sides. So now I end up with theta equals the inverse sine of x minus 5 over 15. Did I use an inverse trig function? Do I have theta equals some stuff with an x in it? Yeah, I'm done. That's it. Yeah, for some reason, that's another problem that people just leave blank, and it's like really, really not hard at all, right? Just use SOHCAHTOA and then use an inverse trig function. Any questions or concerns there? Nope. Sweet. All right. Use a calculator to find an approximate value for each expression rounded to 3 decimal places. All right. So we pull out a handy dandy calculator. All right. All right. So now, because it doesn't specify what it wants the answer in, that being degrees or radians, all right, it doesn't matter, right? I would 100% accept either, all right? In this case, our calculator is already in degrees, so I'll just leave it there. It doesn't matter. If your calculator was in radian, it wouldn't matter. I would accept both answers, right? So all I have to do is inverse sine of 0.7. 44.427 degrees. Right? Or I would also accept 0.775 radians. Right? Now you don't need to put both of those, right? But either one of them would be accepted. Right? So that being said, I'll just only do degrees for the rest of these, but it doesn't really matter. All right, so we can say inverse cosine of negative 0.2. 101.537 degrees. All right, come over to the other side here. All right, now, we don't have a cotangent button, okay? I kind of already went over this with you about why this works, right? But if this is equal to some theta that we don't know, again, you don't have to write this down. This isn't, you don't have to show this as part of your work, all right? But I could just use the regular cotangent. So I would get negative 4 is equal to cotangent of theta. Well, cotangent is the reciprocal of tangent. So I could just say, okay, well, negative 1 over 4 is equal to tangent of theta. And then, of course, I could take the inverse tangent of both sides, right, to end up giving me that theta is equal to the inverse tangent of negative 1/4. All right. So again, you don't need to show these two steps here, right? All you have to do, I do want you to show me this, right? Show me what you're plugging into the calculator. All right. A lot of you are terrible about that when it comes to on your test. You don't show me what you plug into your calculator, so you lose points, right? If it requires, like if it's not something that, like here, you don't have to show me anything because what's on the paper is what you can plug on your calculator, right? But if it's something that you have to alter before you can plug it into your calculator, I want to see that, right? If you don't show me that, you'll lose a point, right? So all you really have to do, right? Again, there was the explanation that you don't have to show. All right, but what I would want you to show is, okay, I know that I can take the reciprocal inverse function and I can take the reciprocal of the argument. Okay, so that's what I want you to show because that's what we're going to be plugging into the calculator. All right, so negative 14.036 degrees. All right, same thing would happen here. All right, we don't have a button on our calculator for cosecant. What is cosecant's reciprocal? Sine. So we just do inverse sine, and then we take the reciprocal of this, so 7 over 12. So that's what we're going to be plugging into our calculator. .685 degrees. And that's it. So that's pretty straightforward. Questions or concerns there? Sweet. All right. Solve each triangle. Round angles to the nearest tenth and sides to the nearest thousandth. Right now, on part A and part A only, and your test is going to be exactly like this, so don't be one of those 2 or 3 students that does this every semester. Right? Part A, it tells you is a right triangle. All of the other ones, it does not say that for. All right? Don't act as if they are all right triangles. They are not. All right? So here, all right, if we label this A, B, C, all right, this is 48 degrees, and side A is 16. All right, so we need to solve the triangle, which means we need to find all of the missing pieces. All right, so I need to find B, side C, and angle B. What's the really easy one? What is it? Angle B, absolutely, right? Because we have two angles, all we have to do is make it so that they add up to 180, all right? So this is obviously 42 degrees. All right, now this is a right triangle, so we can go ahead and use SOHCAHTOA. All right, so I have this piece here, all right, and I'll find B first, all right? So, and I know that this is 42. You could use either angle, but I'm going to use this one because it's going to make it a little bit easier. All right, so if I'm referencing from this angle, this is my opposite, this is my adjacent, which trig function deals with opposite and adjacent. Tangent, right? So I'm going to say, okay, well, the tangent of 42 degrees is equal to the opposite, which is B, over the adjacent, which is 16. So of course here to solve for B, it's easy enough to just multiply both sides by 16. So then we say in our calculator, 16 times the tangent of 42 degrees. You do want to make sure that you're in degree mode, which we are. 14.406. Degrees because the angles that we're dealing with are in degrees, right? All right, now we need to find side C here. There's a couple of ways we could do it. You could use the Pythagorean theorem, a squared plus b squared equals c squared. But if you do that, make sure that you use this whole number and not just the 0.406. You might get some rounding error if you do that. All right. But you could also just use, SOHCAHTOA again. You can either use this angle and say opposite over hypotenuse, or you can use this angle and say adjacent over hypotenuse. Right? So it doesn't matter which one. I'll just use this one so that I use sine. All right. So I will say the sine of 48 degrees is equal to the opposite, which is 16, over the hypotenuse, which is c. So first I would multiply both sides by c, right? Then I would divide both sides by the sine of 48. All right, so we plug that into our handy-dandy calculator. So 16 divided by the sine of 48 degrees, and we will get 21.530. All right, do make sure that you follow the directions here. Round angles to the nearest tenth, all right, so 1 decimal place, and sides to the nearest thousandth, which is 3 decimal places. Of course, we didn't have to round this at all, it was exact. All right, but these two we had to round to the nearest thousandths, like the instructions say. All right, next one. All right, here we have ABC. All right, now it's easy to tell with this one which case, all right, but I feel that it's very important to go over this again. All right, what I would highly recommend you do on your test, all right, or on a piece of scrap paper off to the side somewhere, since you're going to be at home, that would be easy enough. All right, in pen, all right, draw a triangle here and just label it A, B, C. All right, and then you can also do your lowercase stuff. And I know this is annoying and time consuming, but it will help in the long run. All right, so here's our triangle, and just so I can use this on every problem here, I'll copy that thing. Okay, so what we want to do is circle the pieces that we're given. All right, now it's also important to have somewhere that, okay, so law of sines, all right, you do angle, angle, side, angle, side, angle, or side, side, angle. And of course, you have to be very careful with the side, side angle case because that's the ambiguous case. All right. And you use law of cosines for side, angle, side, or side, side, side. All right. Side, angle, side, you use the regular law of cosines formula. For side, 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 all right, you use the alternate law of cosines formula. Okay. So here, obviously, we are given side A, side B, and side C. All right, so that's obviously side, side, side. So I'm going to be using law of cosines. Okay, now law of cosines, the alternate form is the cosine of angle A is equal to B squared plus C squared minus A squared over 2BC. All right, now obviously, to solve for just angle A, we don't want cosine of A, right? We want angle A. We're going to have to take the inverse cosine of both sides. So I'm going to kind of go ahead and jump to that. So I'm going to say, okay, my angle A is going to be equal to the inverse cosine of B squared plus C squared minus A squared, all divided by 2BC. All right, so now we can plug that exactly into our calculator. We say the inverse cosine of A squared plus B squared minus A squared all over 2BC. 29.7 degrees. Remember, angles we round to the nearest tenth. So A equals 29.7 degrees. All right, who remembers every time after we use law of cosines, all right, what are we going to immediately use right after every time to find the next piece? Hint, it's another law. Law of sines, every time, okay? Now, we do have to be careful when we use law of sines after law of cosines, all right, because there's can be that weird problem where if your angle is obtuse, it's going to mess with you. So you always want to find the smaller angle first, okay? So we know that C has to be the biggest angle because C is the biggest side. So we're actually going to go ahead and find side B first, okay? So sine of angle A over side A has to equal sine of angle B over side B. All right, so now we multiplied both sides by 8. All right, and then we're going to have to take the inverse sine of both sides. So now I just plug this into the calculator. So the inverse sine, whoops, there, of 8 times the sine of 29.7 over 5. And that is 52.4 degrees. Again, this is an angle, round it to tenths. All right, well, now we have two of the angles. All right, so we can easily find our third. So 52.4 and 29.7, that's going to be 82.1. So that's going to be 97.9. And it's a good thing we found that smaller one first, because this is an obtuse angle, so that would have messed us up. All right, there we go. All right, our next one. Oops. Whoa. There we go. Okay, so now we want to do the same kind of concept here. Okay, I have side A, all right, I have side B, all right, and I have angle A. All right, well, this is either ASS or SSA. All right, so SSA, we got to be careful. All right, that's our ambiguous case, right? So we're going to say, okay, let's go ahead and find our H, right? So I know that H is equal to, and actually we have to be careful first. Remember, we have to worry about, do we have to relabel these or not? Well, my two letters that match up have to be A, and they are. And my extra side has to be B, which it is. So we're good, okay? So here we're going to use that H is equal to B times the sine of A. All right, so here we're going to say 16.5 times the sine of 75 degrees. All right, so we use our handy dandy calculator to figure this out. So we get 16.5 times the sine of 75 degrees, and we get 15.938. All right, so now we want to go through all of our conditions for our law of sines ambiguous case. All right, and that will be, all of that will be given to you. Of course, you're taking it at home anyway. All right, but I'll post that as a material under classwork so that you have it available to you for your test tomorrow. All right, so the first we want to say, okay, is A less than H? Is 2.5 less than 15.938? Yes. All right, so A is less than H, and that tells me that we have no triangles. We're done. Awesome. That's the absolute best case scenario. You don't have to do any work, really. Yep, you do exactly what I've shown. I need to see the H. I need to have seen you found the H. I need you to give me the condition, and then I need you to tell me how many triangles. All right. Okay. Okay, remember from geometry, when in any triangle, the smallest angle is across from the smallest side. The largest angle is across from the largest side. So we had already found A here, right? So the only two left were B and C. Well, B has to be the smaller angle because it's the smaller side. Does that make sense? Okay. So that's how we kind of determine there which one we want to find. You're welcome. Okay, letter D. All right, so if I do the handy dandy triangle again, so we're given B, all right, we're given little b, and we're given A. All right, so again, we have SSA. Again, this is the ambiguous case. All right, we do have to be careful because my two letters that match are not A, so I have to make them A. And then my extra side, I have to make B. All right, so again, I'm going to do my H is equal to B times the sine of A. So we do that in our calculator. And we get 2.620. All right, so now we can go through our comparisons. All right, is A less than H? Nope. Is A equal to H? Nope. Is A greater than or equal to B? Nope. All right, is A between H and B? Yes, it is. All right, so A is between H and B. So I'm going to have two triangles. All right, this is the worst and most annoying case. All right, so I'll get all this stuff out of here. Why did you not come with me again, Mr. A? Okay, so it's easiest, all right, to separate your triangles. Triangle 1, triangle 2. Triangle 1 you find just like you would find any triangle, all right? Now we know that the ambiguous case is law of sines, so we have to use law of sines. So we say the sine of A, which is 25 degrees, over side A, which is 4, has to equal the sine of B over side B, which is 6.2. All right, so we multiply both sides by 6.2. All right, and then I'm going to have to take the inverse sine of both sides to get my B. And I should be calling this B1 because we're going to have one for triangle 1 and one for triangle 2. All right, so we go ahead and say, okay, the inverse sine of 6.2 times the sine of 25 divided by 4. And that is 40.9 degrees. Remember, this is an angle, just round it to 1/10. So B is equal to 40.9 degrees. All right, well, now we have two of our angles, 25 and 40.9, so we can easily enough find the third angle. So that's 65.9. So that's 114.1. All right, and now I will have to use law of sines one more time. All right, I want to use the two that I was given, so sine of A over A again. So sine of 25 degrees over 4 is equal to sine of C, which is 114.1 degrees, over little c1. All right, so now I cross multiply and divide by the sine of 21 to get that c1 will equal 4 times the sine of 114.1 degrees over the sine of 25 degrees. So .640, all right, 8.640. That's a terrible 8. All right, so there's all three of our missing pieces there. All right, now to start with triangle 2, we always start the same way. All right, B2 is equal to 180 minus B1. All right, so in this case, that's going to be 139.1. remember, the three pieces that were given to us up here are in both triangles. So we have two angles again. So it's going to be very easy to find our third angle. All right, so 139.1 plus 25 is 164.1. So this will be 15.9. And then we use the law of sines one more time. Right, so we are going to say, again, sine of A over A, since that's what's given to us. So sine of 25 degrees over 4 is equal to sine of C, which is 15.9 degrees, over little c2. So again, I'm going to cross multiply and divide by the sine of 25. So c2 will equal 4 times the sine of 15.9 over the sine of 25. So we plug that into our handy-dandy calculator. All right, so this is 4 times. So 4 times the sine of 15.9 divided by the sine of 25, and we get 2.593. And we're done. We found both triangles. All right, so that's the worst case, right? We don't want to have to find two. We'll see. Maybe I'll be nice and not put one of those on the test. Okay. So here we are again. All right, so again, we circle the pieces that were given. I'm given B, I'm given A, and I'm given A. All right, so again, this is SSA. So this is the ambiguous case. All right, so again, and I don't need to change my letters because my two that match are the A and my extra one is B. So I can go ahead and find H, which is B times the sine of A. All right, and that will give us 2.588. So now we do our comparisons. Is A less than H? Nope. Is A equal to H? Nope. Is A greater than or equal to B? Nope. All right. Is A between H and B? Yes, it is. That's the two triangle case again. For time purposes, we just did one of those. All right, and I want to be able to get through more. All right, so that would be two triangles, but we could still say A is between H and B, and say, okay, that's two triangles. All right, here, Control B. All right, again, we circle what we're given. So we're given angle B, side A, and side C. All right, this is side, angle, side. So this is law of cosines, but the regular one. All right, so that's typically it's the one that's given to you is A squared is equal to B squared plus C squared minus 2BC times the cosine of A. That's the one that'll be given to you. All right. But remember, basically, whichever angle we're given, we want these two letters to match up. And then, of course, these have to be the other two, right? So if I'm given angle B, I can just rewrite this as B squared is equal to A squared plus C squared minus 2AC times the cosine of B, right? And now I'll have all of these pieces that were given to me, right? And, of course, I'll want to take the square root of both sides to get B by itself. So now I say, okay, A squared plus C squared minus 2 times A times C times the cosine of angle B. And when I do that, I will get the square root of 10 squared plus 20 squared minus 2 times 10 times 20 times the cosine of 150 degrees. And we get 29.093. All right, now, whenever I use law of cosines, I always immediately follow with a law of sines. All right, I want to find my smaller angle, which because 10 is my smaller side, A is my smaller side, A is going to be my smaller angle. So I'm going to say sine of A over A is equal to sine of B over B. And we have to use this, so it is what it is. All right. So now, and of course my A was actually given to us, which is 10. All right, so now I just multiply both sides by 10. And then I take the inverse sine of both sides. All right, so when I do that, we get the inverse sine of 10 times the sine of 150 over 29.093. And that's 9.9, and because this is an angle now, so 9.9 degrees. Of course, now we have 2 of our 3 angles. We can easily find our third angle. So that's 159.9. So that's going to be 20.1. All right, this is going to be another law of sines ambiguous case. I believe it's just one triangle, all right? But for time purposes, I'm going to skip that, all right, so that we get to the word problems, all right? But if you can find, I mean, it's just finding one triangle, right? So the other one, like where we found 2 triangles, you just don't find the second triangle. You find it the exact same way as we found the first one, and you're done, okay? Okay, so here we have area of each triangle. All right, here we have all 3 sides, so we're going to use Heron's law. So first we find S, which is A plus B plus C, all divided by 2. All right, so that's 24, 36, so 18. And then the area is equal to the square root of S times S minus A times S minus B times S minus C. So we plug that into our calculator. $54. And that would be units squared. All right, here we have the case where whenever you have 2 sides and the included angle, and that always happens whenever all of your letters are different, right? A, B, C. All right, so the formula for that is A is equal to 1/2 times the product of the sides, all right, times the sine of the included angle. So we go ahead and plug that into our calculator. All right, and we get 474.948. Units squared. And of course, those formulas will be given to you on the formula sheet as well. Okay, so 14a. All right, a building 350 feet tall. All right, so 350 feet tall. Casts a 105-foot shadow. If a person stands at the end of the shadow and looks up, right, to the top of the building, what is the angle of the person's eyes to the top of the building? Assume that the person's eyes are 6 feet above ground level. All right, so this is 6. All right, so if I'm just looking at that triangle with the dotted line, right, 350 minus 6 is 344, and this is 105, and I'm looking for this angle theta. All right, well, this is the opposite. This is the adjacent. So what trig function am I dealing with? Tan. So we say, okay, the tangent of theta is equal to the opposite over the adjacent. If I want to solve for theta, how do I break apart tangent? Inverse. All right, so we take the inverse of both sides. All right, we plug that into our handy dandy calculator. Oh, come on. All right, so we do our inverse tangent of 344 over 105, 73.0 degrees. And we're done.
Do we have to add in the 6?
Oh, yeah, absolutely. Yeah, that's the whole point of them telling you that, right? If you didn't have to add it in, they wouldn't even mention it. Oh, no, because you're just finding this angle. There's no, like, you can't add, like if you added 6. Now, if you were looking for this height, you know what I mean? Like if they gave you this angle and you would have found the 344, then you would have had to have added in the 6 to get the height of the building. Does that make sense? But this angle that, you've already factored in that 6 here.
Yes, sir. Thank you, sir.
Yep. Okay. B, an airplane is sighted at the same time by 2 observers who are 1.75 miles apart. All right, so we've got 1.75 miles apart. All right, and there's some airplane up here. They report angles of elevation as 12 and 24 degrees. Okay, well, let's pretend the airplane's up here. All right, so we know that we have 12 and 24 degrees. All right, how high is the airplane? So we want to know this height. All right, you cannot jump straight to it. We did a problem very similar to this in class where this was a flagpole instead of an airplane. We have to find one of these two sides. You don't have to find them both, just one. All right. Now, how we do that is we're going to use our law of sines. Since we know this is 12, this is 24, that's 36. So this big angle here has to be 144 degrees. So now I can use the law of sines to find either of these. I'll just go ahead and find x. So I know that the sine of 144 over 1.75 is equal to the sine of 24 over x. So I would cross multiply and then divide by the sine of 144. So 1.75 times the sine of 24 over the sine of 144. All right, and we plug that into our calculator. Right, and you get 1.21, actually just all of this, right? All right, because we're going to want to use the whole thing to reduce rounding error. All right, well now, since we know x, we can just look at this piece of the triangle. I know this is a right angle because the flagpole isn't leaning. All right, I know that this is 1.21 dot 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 dot, and I know this is 12 degrees. All right, I'm looking for the height here. All right, this is opposite and hypotenuse, so I'm going to do sine. All right, so the sine of 12 degrees is going to equal h over that whole mess. So I multiply both sides by that. All right, so I'm going to get h is equal to, and all I have to do is take this, so I can say times, and it'll just automatically say that answer, times the sine of 12 degrees. So 0.252. And that's miles. And we're done. Hint, you will have a problem just like that on your test. Okay. C. A room in the shape of a triangle has sides of lengths 8, 10, and 11 yards. If carpeting costs $18.50 a square yard and padding costs $4.25 a square yard, how much to the nearest dollar will it cost to carpet the room, assuming that there is no waste, right? So just kind of ahead of time, I'm going to say, okay, well, the carpeting, whoops, plus the padding, all right, is going to be $22.75 per square yard. Okay, so that's going to be my cost per square yard. So now I just need to find the area of the room. Well, it gives us three sides. We can use that Heron's formula, all right, where S is equal to A plus B plus C divided by 2. So that's 29 divided by 2 is 14.5. And then the area is equal to the square root of S times S minus A times S minus B times S minus C. So we plug that into our calculator. And we get 38.528 dot dot dot. 0.528. Well, now all I have to do is multiply this by my 22.75 to get my cost. And it said to the nearest dollar, so $877. And we are done there. All right, and last but not least, find the area of the shaded portion of a circle of radius 13 formed by a central angle of 82. All right, so this is 82, and both of these radii here are 13. All right, now, the area of the shaded region is going to be equal to the area of the circle minus the area of this triangle. All right, so the area of a circle is pi r squared, and my r here is 13. in the area of a triangle, remember, if we have two sides in the included angle, it's 1/2 the product of the sides times the sine of the included angle. So we can just plug that straight into our calculator as you see it. So pi times 13 squared minus 1/2 times 13 times 13 times the sine of 82 degrees, and we get 447.252. And this would be centimeters squared. And that's it. We finished just in time. Any questions or concerns?
Could you go back to the previous slide?
Say that again. Go back to the last one.
Yes, sir. I just didn't see the last number.
Gotcha.
Okay,
Not a problem. All right, guys. That does it for the review.